So in this video we are going to discuss the question in thermal physics which appeared in IIT-JAM examination 2010. The first question is: a gas of molecule each having mass m is in thermal equilibrium at temperature T. Let Vx, Vy, Vz be the Cartesian components of velocity v of a molecule. The mean velocity Vx minus alpha Vy plus beta Vz, its a whole square, is given by. Okay. So before we handle this question, let me give you some important results that you need to remember, and then you can handle this kind of problem very easily. Okay. So in the theory we have learned that the average of Vx, that is equal to average of Vy, that is equal to average of Vz, and that is equal to 0. Okay. And further we also learned that any cross multiplication of two components Vx, Vy, that is equal to Vy, Vz, and that is equal to Vz, Vx, that's also 0. Further, the squared average, that is Vx square, this is equal to Vy square, and this is equal to further Vz square, and this is Kt by m. So you need to remember only these three results. Okay, and with the help of these three results we can evaluate the mean value of the given expression, which is, so we are supposed to find the mean value of Vx minus alpha Vy plus beta Vz, its whole square, and its average. Okay, so this is equal to, just let's open the square. Okay, so this is equal to Vx square plus alpha square Vy square plus beta square Vz square minus 2 alpha Vx Vy minus 2 alpha beta minus 2 alpha beta Vy Vz plus 2 beta Vz Vx, and its average. Okay, so because we are taking the average, so this can be further rewritten as, this is further equal to average of Vx square plus alpha square, because alpha it's a constant, so alpha square we can take outside, alpha square, and then average of Vy square plus beta square and average of Vz square minus 2 alpha and then average of Vx Vy minus 2 alpha beta and average of Vy Vz plus 2 beta average of Vz Vx. Okay, so as I said earlier, because this average, this will vanish, this will also vanish, and this average will also vanish. Okay, so now we can further rewrite this equation as, so average of Vx minus alpha Vy plus beta Vz, its square and its average, this is equal to the average of Vx square, which is equal to Kt by m. Okay, now further plus alpha square and average of Vy square, which is again equal to Kt by m. So this is alpha square, sorry, and then the third term plus beta square and average of Vz square, which is further equal to Kbt by m, and this is equal to 1 plus alpha square plus beta square multiply by kVT by m. Okay, so therefore A is the correct option here. It's correct. Let's continue with the next question. The statement is a trapped air bubble of volume V1 V0 is released from a depth h measured from the water surface in a large water tank. The volume of the bubble grows to 2V0 as it reaches just below the surface. The temperature of the water and pressure above the surface of water, which is given by 10 power 5 Newton per meter square, remains constant throughout the process. If the density of water is 1000 kg per meter cube and the acceleration due to gravity is given as 10 meter per second square, then the depth h is okay. So let's try to represent this problem. So we are given a situation where a air bubble. Let's draw the tank so that we can understand it in a better way. Let's assume that its height is h. Its height h basically it represents the water level inside the tank. Okay, so here we are having water here. So we are having a air bubble here whose volume is V0. Okay, and this bubble it's rising in the upward direction and it's reaching at the surface, but then its volume it's changing into 2V0. Okay, now if we assume that let this height be h, so this is basically the height of the water column in the tank. Okay, and it's further given that the pressure, the atmospheric pressure which is acting at the surface of water, that is equal to 10 power 5 Newton per meter square. This is also given to us. Okay, now this air bubble it's moving from from the surface of the tank, the bottom of the tank to the surface of the the water level. Okay, and its volume it's doubling, and it's further given that temperature doesn't change. Temperature of the water it's fixed. T is fixed here. Okay, and the outside pressure it's also fixed. Okay, now what else information is given to us? The density of water, raw water, that's also given to us, that is 1000 kilogram per meter cube. Okay, and acceleration due to gravity, that is 10 meter per second square. Okay, now we have to find what is the height h of the water column. Okay, and T water, that's also given. T water, that is constant throughout the process. So that means it's the like a isothermal type situation, isothermal. Okay, now the pressure at the bottom of the tank is given by pressure at the bottom of tank. Okay, so this is basically how much will the pressure at this point on the air bubble. So this is basically the atmospheric pressure plus the pressure exerted by the water column whose height is h and density is 1000 kilogram, or you can say the raw water. Okay, so that means this is equal to the pressure at the bottom of the tank, that is equal to the atmospheric pressure, which we are calling as P atmospheric, plus the pressure exerted by the water column whose height is h, and that is given by, so this expression we have learned in elementary classes, rho g h. Okay, here this is the basically the pressure exerted by the water column, pressure exerted by water column of height h. Okay, now because the temperature of the water it's not changing, so that means we can assume the process to be isothermal in nature, where volume is changing from V0 to 2V0. Okay, so that means if we assume the air to be an ideal gas, if we consider the air bubble to be an ideal gas, so that means we can apply that equation PV is equal to PV, that is equal to nRT. And because the T it's not changing, so then N it's also going to some constant quantity, and R it's already a constant. Okay, so that means at this point this equation will be valid for the that air bubble, and at this point also this equation will be valid. Okay, so that means at the bottom at the surface of the water, this relation will give us P atmospheric, the pressure at the surface, multiplied by the volume of the air bubble, which is 2V naught, PV, and that will be equal to nRT. Okay, so and at the bottom we have P, the pressure, corresponding pressure, which is P atmospheric, plus the additional pressure exerted by the water column, which is rho GH. This is the total pressure at this point. Okay, multiply by the corresponding volume of the air bubble, which is V naught. Okay, so this will be valid. Okay, so after rearranging this expression, so V naught will cancel with V naught. So from here we can conclude that rho GH, that is equal to 2P atmospheric minus P atmospheric, which is nothing but P atmospheric. Okay, so from here we can find the height of the water column, which is equal to P atmospheric divided by rho into G. Okay, so P atmospheric is 10 power 5 Newton per meter square. Okay, divided by the density of the water, which is 1000 kilogram per meter cube, multiplied by the acceleration due to gravity, which is 10 meter per second square, and this comes out to be equal to 10 meter. So therefore height of the water column is 10 meter. B is the correct option here. So let's continue with the next question. The statement is, a particle of mass m is confined in a two-dimensional infinite square well potential of side A. Okay, the eigenenergy of the particle in a given state is given as given by this expression. The state is, so we have to identify the correct option out of given 4 options. Okay, so let's try to understand this problem. So we are given a two-dimensional infinite square well potential whose side is A. So for a one-dimensional infinite square well potential, the energy eigenvalues, if we consider the potential along x direction, so I am denoting the energy eigenvalue as Enx. Okay, so this is equal to nx square h square upon 8m a square. Okay, where nx can take values from 1, 2 and so on. Okay, now for the two-dimensional potential well, the energy eigenvalues can be written as Enx ny, and that is equal to nx square plus ny square. Simply we are adding another energy terms along the bidirection and multiply by h square upon 8m a square. Okay, and this can be rewritten in the form which is given here in the question. Okay, this is equal to n x square plus n y square upon 2m a square, and then h cut square pi square, where we have taken h cut, h cut is equal to h upon 2 pi. So this result can be easily obtained after rearranging all the terms. Okay, now what is given to us, so let's call this as equation 1. Now what is given, E, the energy eigenvalues, they are given to us 25 h cut square pi square upon m a square. Okay, so when we compare equation 1 and 2, we obtain, comparing 1 and 2, or 1 and 2 implies that nx square plus ny square divided by 2, and that is equal to 25. Okay, so this implies nx square plus ny square is equal to 50. Okay, now so we have to make the possible choice for nx and ny such that this condition is satisfied. Okay, so the possible nx and y values, are either 1, 7, where nx is 1 and ny is 7, that will give us nx square plus ny square, that is equal to 50, or the second choice could be 7, 1, and the third choice could be 5, 5. Okay, so for these three combination of the value of nx and ny, this condition will be satisfied. Okay, so therefore given energy level is threefold degenerate. Okay, so for these three different value of nx and y, the energy of the particular level, that's going to be same. So therefore it's the B is correct here. So let's continue with the last question. The statement of the question is 1 mole of an ideal gas. So we are given N is equal to 1 mole in an initial state A with pressure Pi and volume Bi is to be taken to a final state D. Okay, so we have to carry out a process from this point A with parameter Pi Bi to the final state, which is denoted as D here with pressure and volume as Pf and Vf. Okay, with Pf, so it's given as the Pf and Vi, they are connected to this relationship. So we are given that Pf, that is equal to Vi upon B. Okay, through the path A to B, B to C, and C to D as shown in this figure. Okay, below for the particular value of V greater than 2. So value of V, it's given to V, it's greater than 2. So here process A to B and C to D, they are given to be adiabatic. So that means this is an adiabatic, and this process is also adiabatic. Okay, it's given. Okay, so these are the adiabatic path, while process B to C is an isotherm. So this process, this intermediate process, this is an isothermal process. Okay, with temperature T naught. Okay, so that means this is an isothermal process. Okay, states B and C corresponds to P1 V1 and P2 B2 respectively. Okay, find the, so we have to find two quantities. The first is find the ratio. What is ratio B2 by B1? That's our first task. And the total work done by the gas in terms of Pi, Vi, T naught and V naught. Okay, so so we have to find these two quantities. The second is total work done. So we will continue with the determination of B2 by B1. Okay, so we will we will start developing our solution with the given information. So it's given that because process AB and CD, these two processes, they are adiabatic in nature. It's given these are adiabatic processes. Okay, that means what? So that means the relationship that connects the two equilibrium states when the process is occurring, it's adiabatic in nature. So then PV power gamma, that will be constant for those two equilibrium states. Okay, so that means here for the point A, the parameters are, the thermodynamic variables are Pi, Vi. Okay, so that means at point A, Pi Vi power gamma, because it's an adiabatic process, that should be equal to, because the point B, this is also lying on the process AB, which is adiabatic in nature. So that means this is equal to P1 V1 power gamma. Let's call this as our equation 1. Now similarly, process CD is also adiabatic in nature. So we will apply the same equation here. So here for this point D first, we will write PF Bf power gamma, that is equal to, the coordinates of the point C are P2 B2. So that means P2 B2 power gamma. Okay, let's call this as equation 2. Okay, now the third process, which is BC, that is isothermal in nature. Okay, process BC is isothermal. That means if it's isothermal, so that means PV is equal to nRT, that will be satisfied. Okay, so if we apply this, because its temperature, it's constant during this process, N is also constant, R is also constant, so that means between these 2 points, that is point B and point C, this equation will be valid. Okay, so that means point B and C, they are connected by this relationship P1 V1, that is equal to P2 B2. Let's call this as equation 3. Now we have to find B2 by B1. Okay, so from equation 2 and 1 we can obtain B2 by B1 by simply dividing equation 2 with equation 1. So let's do that. So basically we are now finding the solution for the part 1. Okay, so divide equation 2 by equation 1, then we obtained, if we divide this PF BF power gamma divided by PI VI power gamma, that is equal to P2 B2 power gamma divided by P1 B1 power gamma, and this is further equal to, so I'm rewriting this this result basically P2 B2 multiplied by V2 power gamma minus 1. So okay, so I have splitted basically the numerator, and I will do the same thing with the denominator also, P1 B1. So I'm doing it intentionally so that some of the quantities, they will cancel with each other, B1 power gamma minus 1. So P1 B1 will cancel with P2 B2 because of this equation 3 here. Okay, so we are left with simply this is equal to B2 upon B1 power gamma minus 1. Okay, now because it's given to us that, let's call this as equation 4. Now we are given that BF, that is equal to VI divided by B, so it's given here. Okay, and also PF is equal to B square PI, which implies PF upon PI is equal to V square. Now we will make use of this result in equation 4, so that we can rewrite equation 4 as, so put these values in equation 4, then B2 upon B1 power gamma minus 1, that is equal to PF VF power gamma. So now we are going to substitute these values here. Okay, so because PF is equal to what you can say is PF upon PI, that is equal to B square. Okay, so here I'm going to replace PF upon PI here in this equation. I'm going to replace this as B square directly. Okay, so this is equal to B square and then multiply by BF power gamma or BF upon BI power gamma. Okay, so BF upon BI power gamma, that is equal to 1 by B square basically. Okay, B2 by B1, BF, that is equal to BI power gamma upon or B power gamma, and then multiply by 1 upon BI power gamma. So basically this is BF power gamma and this is 1 upon BI power gamma. Okay, so I wrote them separately, so this will cancel with each other. So this is equal to B power 2 minus gamma. Okay, or I can rewrite this as B2 upon B1, this is equal to B power 2 minus gamma divided by gamma minus 1. Now let's move to the next page. Okay, and if okay, so let me solve it here. So if I plug in the value of gamma, because the gas which is given to us, it is the monatomic gas. Okay, monatomic gas, so that means for the monatomic gas gamma is equal to how much? Gamma is equal to 5 by 3, and if we substitute the value of gamma here, we will obtain this equal to the power, the exponent of the V will be simply 1 by 2. So simply what you have to do is simply substitute the value of gamma here in this expression, and after solving we will find that exponent turns out to be equal to 1 by 2. Okay, so this is our final result for the first part. So that means what we have obtained is B2 by B1 that is equal to under root B. Okay, now the second part, the work done. This will we have to calculate the total work done during the entire process. Okay, so we will do it in different steps. So the first part that we will consider the process AB. So if you just take a look at the picture that is given to us, process AB is it's an adiabatic process. Okay, so here the work done in an adiabatic process, you should remember this result. The work done in process A to B, which is adiabatic in nature, this is equal to 1 upon gamma minus 1, and inside we were having P1 V1 minus P2 B2, where P1 V1 corresponds to initial state, and here the initial state corresponds to thermodynamic coordinates with Pi and Bi values. Okay, so that means I will write here Pi Vi minus the coordinate of the final state, which are P1 V1. Okay, so this can be further written as 1 upon gamma minus 1 Pi Vi minus P1 V1, that is equal to R T naught. So I can write this as P1 V1 equal to RT naught, because this point is also connected with the isotherm, which is at temperature T naught. So because this point, this point, okay, this is connected with this isotherm BC, which is at temperature T naught. So that's why P1 V1 will be nRT naught, but N is given to be 1 mole. So that's why we are replacing it with RT naught. Okay. And if you substitute the value of gamma here, because gamma it's 5 by 3, it's monatomic gas, so then this comes out to be equal to 3 by 2 Pi Vi minus RT naught. Okay, so this is the work done during process A to B. Now similarly we can evaluate the work done in process B to C. So the second part, process B to C, which is isothermal in nature. Isothermal process. In isothermal process, we know that the work done is given by WBC, which is isothermal. It's given to us. It is nRT naught. N is 1, so I will write only RT naught, logarithmic of natural logarithm of final volume, which is B2 upon V1. Okay, so let me show you the picture again so that you can understand it. Okay, so this process B to C, it is isothermal in nature at temperature T naught. Okay, so the coordinates are changing from P1 B1 to P2 B2, so therefore the work done is given by this expression. Okay, so but now B2 by B1 we have already calculated, so it's here. So if we substitute the value of V2 by V1, so this comes out to be equal to RT naught ln under root of B. Okay, so this is nothing but RT naught by 2 ln B. Okay, so this is a second expression for the work done during process BC. Now we are left with the third step and last step, which is process CD, process C to D, which is again adiabatic in nature. Adiabatic in nature, and the coordinates, the thermodynamic coordinates changes from here during this process, changes from P to B2 to P final and B final. So therefore work done during this process, as we wrote in the first process, AB W C to D, that is equal to 1 upon gamma minus 1, coordinate corresponding to the initial equilibrium state, which is P2 B2 minus coordinate corresponding to the final equilibrium state PF BF. So again I can write the product of P2 B2 as RT naught, because n number of mole, that's 1, and this point, this equilibrium state is again at the temperature T naught. Okay, so that means, and if I further substitute the value of gamma also, so this comes out to be equal to 3 by 2 multiply by RT naught, and then substitute the value of PF. What is PF? That is B square Pi, and then Bf, because these values they are given to us in the statement. It's Bi upon B. So I have simply substituted the given values. So this comes out to be equal to 3/2 RT naught minus B Pi Bi. Okay, so let me check the equation number I have given up to 4. Okay, so let me call this as equation 5, and the work done during this process, let me call this as equation 6, and this as 7, and this as 8. Okay, so because we have to evaluate the total work done, and total work done will be given by W total during the entire process, that will be given by the sum of equation 6, 7 and 8. Okay, so that is equal to WAB plus WVC plus WCD, and if we add all these three quantities, so you will see that some of the quantities will cancel with each other, and only we will be left with, I am writing the final answer here, RT naught by 2 ln V plus 3/2 PIVI 1 minus B. So that is the total work done during this process.